Hello, everyone. Thank you to MIF++ seminar. Today, Professor Luigi Vitagliano from Italy, Napoli, will talk about the fine structure of proteins. Over to you, Luigi, please.
Okay. So thank you, Vitaly, for this kind invitation. It's a pleasure for me to share with you what we do about protein. And so since I don't know if I got the right feeling of what would be helpful for you, and I just, since we have likely have different backgrounds, I will start with a very basic presentation of what we do in general, what we do with databases and so on. So let me put it in presentation mode. Do you see the screen? Okay.
So, yes, it's the full screen mode now. Yes.
Yeah.
Okay.
Is it fine? Okay. So just as I said before, a small presentation about what we do here in Naples. We are in the National Research Council of the Italian ministers, and you see we work on protein structure, essentially on a very complex system in molecular terms. We also work a little bit on, this is an area on biomaterials. We look at how peptides, for example, they form supramolecular structures, and then they can be, they can aggregate, form assemblies that are important for some kind of applications in biomaterials. So we do that. We work on these fields. Do you see my pointer? Do you see the pointer?
Yes, it's moving.
Yeah.
Okay, thank you. So we do that by using different strategies. We use both computational approach and experimental approach. And about computations, we do molecular dynamics, molecular modeling. Of course, now that they are in the AlphaFold era, we do a lot of predictions by using this machine learning approach. And but also we do some small data mining, trying to get information from what other people have been deposited in these databases. We also have actually a strong background in the experimental part. We are essentially crystallographers, as our main expertise is X-ray crystallography on proteins. We do, of course, molecular biology to get sample for crystallization. We do some spectroscopy and, in general, biophysical characterization, and we do also some functional studies. So this is a list of the too many systems we work on. There are really too many, probably. And you see, since we use a rather basic approach to the protein structure, we apply it in different systems. We are not focused on a specific for example, a biological pathway. We are, we jump from one subject to the other, but our goal is always to get structural information and to relate structure to function. So this is what we have done recently. Using data by data mining. We have done some, we look for new, the effects of the naturans of protein structures. We look, for example, for new secondary forces that stabilize proteins. We do also some analysis of new local structural motifs. We also have been done some search for understanding the structural determinants of the propensity of residues for specific secondary structure of proteins. We do also some sequence analysis, for example, on SARS-CoV-2, and at the very end, we also do the what we call the fine structure of proteins, that is the subject of the tour. So this is the outline of the presentation. So we will go, as I said, it will be very basic in the first parts. So I will go through just a brief overview of the structure complexity and molecular complexity of biological macromolecules. We'll go to the so-called structure function paradigms, and then we go to the protein structure determination and validation. And in this part, this will be our contribution, which kind of fine details protein structure can reveal, how these can be used for protein quality assessment. There is also the last part, but I don't think there will be time to go in this further in the time that's organized for this seminar. So in principle, molecules, as you know, molecules can be, molecules of life can be divided in different classes. If you just look how different is the structure complexity, you see that most important molecule for life is water, and it's quite simple. Then of course you can get organic molecules that have sites, you know, they have tens of atoms. But if you go to protein, then things change a lot, because you see, if you write the formula, the chemical formula of hemoglobin, which is a rather standard protein, it's not very big, it's a normal protein. You see that, you know, things, we are not used to look proteins in such a way, they are quite complicated. And just to get the feeling of how nature is complicated is that these whole bunch of atoms, they are actually, they transport the oxygen in the blood. But so to transport a biatomic, a molecule that's made, the oxygen is made by 2 atoms, you know, nature uses about 10,000 atoms. I mean, this tells us that, you know, nature is quite complicated. There are some reasons that are random, because of course the evolution does not have any a priori purpose, but also because proteins do much more than the simple biological function we are used to, because they interact with each other. They have to do many other things that we don't, because often we don't know, or often we overlook. So
Luigi, sorry, could I ask a basic question here on this molecule?
Yes.
So for water molecules and glucose molecule, these pictures show explicitly, I guess, so-called covalent bonds between atoms, right?
Yes.
In a protein such as hemoglobin, we already cannot see these covalent bonds. I guess were also present, but I'm wondering if you could maybe briefly describe, there are probably other non-covalent bonds that keep that big molecule in a shape.
Yeah. Well, usually proteins are essentially made, actually I had some, unfortunately I do not have this kind of videos, but proteins of course are made essentially, the overall structure, the atoms are linked by covalent bonds, most of them. Hemoglobin is a special case because in addition to the polypeptide chain, the chain made by residues, by amino acids, you also have a prosthetic group, which is the heme group, which has an iron atom, which is a metal, the iron inside, and the iron makes a sort of bonds which is called coordination bonds with the heme group. And then actually this iron atom, which is, you know, attached, it's not a part of the backbone of the protein, because it's a metal, actually is actually the real atoms that binds the oxygen. So the oxygen is coordinated. Well, coordination bond is something that, you know, it's different from covalent bond. It has some analogies with covalent bond. Then, of course, in the structure, you have a lot of what stabilizes the protein are the non-covalent interaction between different parts of the molecule that gives to the molecule a shape. And so you have something, atoms, and most of the atoms are linked by covalent bonds, but then there are many interactions between these chains, and this interaction makes actually give rise to a defined shape, which is very important, because atoms are brought together for the reaction, for example, and also they have a shape and they can interact with each other in these partnerships that proteins make. So, so let's say again, proteins have a chain which is made by covalent bonds. Then but the overall shape depends on the non-covalent interaction between these atoms. Hope this is clear. Is it?
Yes, thank you, Luigi. Thank
Yeah.
you.
Of course, if you look to the DNA, then, or the nucleic acids in general, then you have a much larger molecular complexity, because each chain of the DNA can be made by millions of bases. So, if you write down the formula, you get even larger number in terms of number of carbon or oxygen or phosphate or phosphorus you have in the structure. But for example, at least for DNA, the structure is quite regular. Everybody knows about the double helix. So the structural problem about DNA is a little bit simplified by the fact that this molecule actually has a sort of regular structure, which is double helix. Different things is about the RNA, but this is not will be a subject of this. So we have the so-called structure function paradigm, and then we will show very briefly what does actually means and how is important even for water, which are something that we consider too simple, but it's actually very important, and the function of these molecules depends on the structure. So the idea that molecules were not just an ensemble of atoms, but that also how they were localized in the space was important, actually is something that dates back, 1.5 century ago. So in this time, in the second half of the 19th century, chemists start to believe that it's not only important to understand which atoms compose a molecule, how they are linked, which atom is linked to the other, but also how they are in the space. Sorry? How they are in the space. So this was, the very first start of what's called structural chemistry. And even for water, as I said before, water is quite simple. You have an oxygen atom, you have two hydrogens. If you apply this code, which are VES Pierre rules, then you can easily understand, because this is a repulsion between electrons, you get this kind of shape. So water molecules is made by three atoms, but it's not linear. And the fact that it's not linear, but it's bent, like it's shown here, makes, since the oxygen is more electronegative than hydrogen, then electrons stay close to the oxygen more than toward the hydrogen. So you have a negative pole in this direction and a positive pole in this direction. So water molecule is a dipole, but this depends only because it's a bent. If a water molecule were linear, then the positive and negative charge, the center of positive and negative charge were coincident. So the molecule would not have been dipole and polar. So you see, the fact that you have this kind of dipole in water makes the water able to perform its action, because if it has to interact with the positive group, it can expose its negative pole and so on. So even in the case of the water, the fact that the water is not linear, but it's bent, has important consequences on its function, in its ability and its properties. Of course, the same is for proteins. Here we have, of course, they can assume very, very even aesthetically nice shapes. You see some examples here, but those are pretty well known protein structures. And but if we want to understand how they work, we can go to the basic example, which is hemoglobin. Hemoglobin, again, is a protein that binds the oxygen. What happens? This is if the hemoglobin is mutated, and you see here there is a glutamic acid, which is a negatively charged residue on the surface of the protein. If this residue is mutated to a valine, you see, out of the 10,000 atoms, you change very few atoms here. You see, these are carbons here, these are also carbons. There are minimal differences, few atoms change. Then the property of the molecule changes, because this is an hydrophobic residue. So if you put here on the external of the molecule an hydrophobic residue, it becomes sticky. And what happens is instead of having tetramers of immunoglobulins separated from one from the other, they just get, stuck one to each other. They form a sort of polymer here, and this change the shape of the erythrocytes that contain a lot of hemoglobin, and then this is a disease quite common in Africa, for example, which is called sickle cell anemia. So this was the very first disease for which a molecular basis was discovered, and then also the structural base, because we know that all the disease is caused by this presence of the hydrophobic group that makes the surface of the molecule a little bit more sticky, and then you get a polymerization of the hemoglobin rather than having single isolated tetramer. So this, shows you how important is understanding the chemistry. So that means the sequence of the protein, but also how important is the structure, because you can understand what actually happens in a pathological state. This was one example, but sometimes effects are even more subtle. You have very, very small variations of the location of some atoms inside the protein, and then the property of the protein will change, and then the effects, the physiological effects. Proteins, as you know, they can be enzymes, they can have many, many different functions in living organisms. They can change also if the position of some atoms change for a fraction of angstrom or even less. So one problem with proteins is that they are very complicated from a chemical structure point of view, because they are made by thousands of atoms, but also you cannot, you have to understand perfectly more how these atoms are located. So errors in the location of atoms can cause problems in understanding how they work. So this was another example. We'll see later how important is the geometry of the binding of some ions. Here there is a binding of the phosphate on the arsenate, but we will see later, and how very, very thin differences make the protein able to bind the phosphate and not to bind the arsenate, which is a venom for our organism, and how the protein is able to discriminate between two very similar ions. I hope this is clear. Is it? Or
so yes, Luigi, very interesting pictures. So maybe this question is a bit earlier, but could I ask if all these local angles that help protein to keep its shape, are these all angles known? At least range.
Yeah, no, we will see this in the lecture later, and then we also discuss a little bit more about this thin difference that is here. I mean, this, you see, this is a paper that was published. Actually, I cannot see the best part. I have to move.
Nature 2012.
Yeah, so it was a quite important, because they show that, you see, this bond here between these angles, we can anticipate the concept, should be as close as possible. This involves in hydrogen atoms. Hydrogen atoms, we'll see, they are quite difficult to see because in the electron density maps of by X-ray crystallography, because they have a single electron, so they do not scatter a lot. So they are difficult to locate. And actually, since they have these very high resolution structures, they claim that the difference in binding the phosphate rather than the arsenate is the fact that binding with the phosphate is more linear. This bond, is as strong as possible if it's close to 180, and you see it's a little bit closer here to 180 than when it binds to arsenate. So the binding with the arsenate is not optimal, and this is why this protein is able to recognize the phosphate, which is important for the physiology of the organism, and not this one, which can be dangerous for the organism. So it's very, very, very thin. In this case, it's very, very, very thin feature that makes the discrimination between two ions. Okay, so this is just to convince you that the structure is important, but also verifying details may be important, because in our era of structural biology, we are used about shapes, but shapes, of course, they are important because they can tell us how proteins recognize each other. they are important for recognizing the partnerships that they establish and all these kind of things. But if you want to understand how really a chemical reaction occurs and when they are, for example, mediated by water molecules, by proteins, enzymes, and so on, you need very, very thin details. Now, how we can get a detailed picture of such large molecules? That's the big problem of one of the problems of protein crystallography, for example, or of structural biology in general. So I don't know why it's not. Okay, so one question is that protein structure, they may be appealing, they can, can give a lot of information, but they, of course, cannot be perfect. So they do contain errors. In general, they cannot be accurate as the user can believe. So protein structure believe that the atom is there, but you have to know whether the atom is actually there and which are the possible error and troubles behind it. So this is a situation that is actually, this is a little bit, a couple of years old. You see, those are the structures that are reported in the PDB. Here you see there is the fraction. Here the gray one is the fraction of structures per year that have been solved by X-ray crystallography. You see that X-ray crystallography is still the most used technique for point structure determination. This is the fraction of the NMR. You see that the fraction of NMR is going down in last years. And here, in orange, you see that the growing of the structures that are solved using cryo-EM. Of course, now there is also the prediction by AlphaFold and all this stuff. But this is, we are talking about the experimental approach solved for structures. So just as a comment on that, the impact of cryo-EM is impressive, not just because they are increasing, but also because they are able to solve complexes of proteins that are made by 100, probably 1,000 atoms. So even the complexity that can be solved by using cryo-EM is quite impressive. But the most used technique is still the X-ray, and what is important is the X-ray always provides us the best available model, depending on, of course, on the resolution. So the best models in terms of accuracy of the coordinate errors and so on are still the X-ray, those obtained by X-ray crystallography. So X-ray crystallography, very basic concept. Of course, you know this. I don't know if this is informative, but this is the difference between diffraction and this is imaging. Unfortunately, we have a sample that in case of X-ray crystallography is a crystal. We will see later how protein crystals are. Then X-rays are scattered by the electrons present in the sample, and then you get the scattering. Like, for example, the ice is diffused by our sample. But then in the case of light, we have lenses, and then we can focus back the scattered waves of light, and then we can have an image. In the case of X-ray, we don't are in such a situation. There is no material that's able to focus the X-rays. So we stop in this position. We are just scattering, and then of course, using the law of interference, we get some spot in some position, depending on the location of the electrons inside our sample. We have spots somewhere, and then we have, here we have constructed interference where we have spots, and then we have nothing, or in other places where the waves cancel each other.
So, Luigi,
yes.
On your previous slide,
Yeah.
Just a comment that says a little more about X-ray crystallography. Years ago, I took a course in Fourier optics, and in Fourier optics, in your image on the right rather, if you had a point source, of course, the lens is going to image it as a point. But if you draw the rays, what you find is, of course, the central line just goes right through, but one that goes farther out has a longer path. And the function of the lens in terms of the wavefronts of light is to adjust the number of waves in that path to be the same. And so then you understand this exactly in terms of the Fourier transforms and the phase. And of course, in X-rays, we don't have the lens.
Yeah, exactly. I mean, this is a very, very simplified version.
Yeah.
And just to say that we do not have image of the protein. We don't have image of the protein. We just stop in the first part because we don't have lenses. This is not the same for cryo-EM, for example, because you use their electrons as waves, because of course they behave as waves as well, the electrons. But then since they are particles, they are charged, you can focus the magnets, so you can focus back in a way that's, roughly similar to the lens. So you get image from those kind of. In the case of X-ray, you are stuck to this. I mean, you have to interpret this in some way to get the image of your product. And this is done in many different ways. But in the case of proteins, there are many problems which are related to the fact that protein crystals are quite specific. They have a number of properties we will see now here. These are some protein crystals. Protein crystals are very particular because they have a high content of solvent. So, you can imagine they are solid, but they are very large channel inside. Most of the crystal is made by the solvent, usually water, or the solution you use to crystallize protein. This is important because it has a lot of good advantages, because in some sense you can think that the protein still fills the environment that is filled in solution, because there is a lot of solution of solvent around in the crystal state. But there is the question that, of course, the presence of the solvent makes the molecule in the crystal that should be perfect in terms of translation. This is not much better than me probably. Of course, you can get small reorganization from one unit set to the other. I mean, this is will represent a problem in the overall order. And what happens in proteins is that sometimes you don't get diffraction at high resolution. This is, if you have to imagine here that the beam is perpendicular to the plane here. So these spots are low resolution, and this one is what's called high resolution. And so you see that this is a typical case in which you see diffraction here at low resolution, and then you don't see diffraction at high resolution. This means, in other words, that you miss information here. So in the case of diffraction by protein, you have a rather limited number of spots, which we will see, actually not much details, represents the experimental information we use to build the model. So of course, I cannot go into details, but this is the, a sort of cycle that is used for, to determine the structure. So this one is the diffraction pattern. From this diffraction pattern, we can get from the intensity of the spots here, we get what's called the structure factor. And then the structure factor, actually, we got, unfortunately, we don't, as Professor Andrew said before, in this case, we don't get the phases. We lost the phase, so we get only the module of these structure factors. But if we had all of these, then we can do the anti-Fourier transform to get the electron density. And then from the electron density, you can put the atom inside the electron density. Then how to solve the phase problem, it's something that really a bit complicated. There are many different methods. But the idea here is that your information comes from the X-ray diffraction pattern. So the number of points here represents the number of terms you have in this expression of the electron density. And of course, we reflect the accuracy of the electron density of the model you built in. Here you see some examples. This is a residue in a protein, and how it may look for a structure that has a 3 angstrom resolution, or it has a 1 angstrom resolution, which is much higher. You see here much more details. You see atoms, the spherical shapes of the electron density tells you where atoms are. You just see where more or less the plane is.
Luigi,
so because
Luigi,
here, of course, we used much. Yes.
Could I ask another basic question on that slide? this collection of structure factors, is this information equivalent to the powder diffraction pattern or not?
Powder diffraction factor. Well, I don't think so. I mean, in the power diffraction, you get, well, I'm not an expert about power diffraction, but of course, in power diffraction, the crystal leads are oriented in several ways. So you don't get spots, you get rings, of course.
I see.
So you miss part of the information because you do not have a unique location of your unit cells, but you have all the mixture. So you get information about the spacing, the resolution, but not how the cell is oriented. And then you do different interpretation with the powder diffraction. So usually powder diffraction is an ensemble of rings. So of course they have much more overlap. If you are interested in it, I can tell you that there's been, I think 15 years ago, I think that with the license design, which is a prototype for X-ray crystallography of proteins, I mean, they've solved the structure using power diffraction data from license design, for example. I mean, there are very special applications, but usually these are called single crystal because you use, I mean, the images obtained here in the experiments, you have only one crystal. In the case of powder, you get many crystals randomly oriented because they are powder like crystalline state. So,
Luigi, so powder X-ray diffraction pattern is weaker, provides only weaker information than the single X-ray diffraction, right?
Could I say here that in the picture of the diffraction pattern in the middle of the screen right now, if you want to see what that looks like as a powder pattern, you simply draw a circle through every single point on there. And
because it's like, exactly.
You can weight the circle by the intensity of the spot.
Yes, thank you.
Because you have crystals oriented in all ways. So each orientation gives you a spot, but then if you sum up, you get, and what remains is just the distance, which gives you the resolution of the spot. I mean, the spacing, there's many different ways in which it can be defined, which means they have fixed distance from the center. So you have rings.
So this collection of structure factors is essentially equivalent to a single X-ray diffraction pattern.
Yeah, we use, there are, of course, also in this case, many applications. In this case, we use, we are discussing about single wavelength X-ray diffraction. Then, of course, because you use a monochromatic X-ray radiation, you can use, there are some experiments in which they use, which is called Lauer diffraction, in which they use a polychromatic radiation for the X-rays. Then, of course, they get an overlap of everything because you get simultaneous diffraction for depending on the orientation of the crystal, but also the wavelength of the X-rays. And then you have to deconvolute all. But if you want to make a very quick data collections, that means microseconds, for example, then you use Lauer diffraction because you collect all data together. Then, of course, they are overlapped. You have to deconvolute. It's a different situation. But there's some analogies with
so Vitaly, the structure factors are basically the square roots of the intensity.
Exactly.
Plus some geometric factors.
What geometric factors?
There's some geometric factors related to the polarization, just like you see the polarization from the surface of light, and there's a couple of these things, and any standard crystallography book works about in a line or two.
Exactly. I mean, that's just the square of the intensity, and then there is a correlation. Then, of course, there are some, when you do the data collection, you make a lot of different correction. There is absorption. There are many different things. Of course, you have, for example, different backgrounds here for the spots. Depending here, you have a high background because here there is a scattering of the water. Because of course you have water, so this is sort of water is not randomly oriented here. So you get this high scatter here, and then of course you have to correct the scatter. I mean, there are many, but they are all of them are automatically made by software. And then from this one, you get from the square of the intensity, you get this part, the structure part. You miss this part. But if you had everything, then you can calculate the electron density, and then you can start to build the model means that you put the atom inside of the electron density. So so if you have this is structure we made many years ago, we got very high resolution, very unusual resolution. In this case, you see atoms are separated. You see they are really separated. The electron density, you can determine the electron density for each atom. You see many other things. You see the hydrogen atoms and so on. So if you go to very, very high resolution, this is very unusual for proteins. But you can get crystals that are particularly stable and particularly ordered that give you this kind of diffraction. You can see details, and you are approaching, you are still not close to, but you are approaching the accuracy you get with small molecule X-ray crystallography. So, which is the main problem in protein structure refinement? So what you do at this point is that, as we have said before, you have the experiments from the intensity, you get the observed structure factors, then you build a model, and then there are formulas from the coordinate of the atoms in your models, and from this one, which is called B factor, which is a terms that describes the vibration of the atom inside, so gives you some idea of the mobility of the atom inside the crystal. Then from your model, you can calculate the also structure factors. So you can compare the structure factors that are fixed because are your experiment, this one with this one. And what you can do in general is sort of you can think to minimize the difference between this one and this one. This, of course, is your experiment. This is a model that can be changed. You change the coordinates, so you change the calculated structure factors, and then you minimize the difference, right? So this means that in principle, you can optimize the similarity between these structure factors, the observed one, which is your experiment, and your model. Of course, the best is disagreement and better your model. Is this clear?
Luigi, what is W with coefficient W of H?
Okay, this is sort. We will see it a little bit later. This one. This is just it's not important. It's just a weight. We will see later. So, in general terms, you see that you can change your model. This will change your calculated structure factors in such a way that this difference will be minimized. So that means that your model has calculated structure factors that are as close as possible to the ones that you are experimentally measuring, right? Okay, so when you have done that, why these things are not so simple? Oh, I don't know. Okay. One problem that occurs with the protein crystallography, which is the most important problem in the refinement step, is that you have a lot of atoms, as we said before, and then crystals do not diffract at very high resolution. So you have a lot of atoms, that means a lot of parameters to be determined, but also, and then you do not have enough experimental data. Usually, in crystallography, they say, I don't know, this is a sort of rule of thumb, that you need at least 8 spots, 8 structure factors for each parameter you have. Usually, when you do small molecule crystallography, you have even 10 of them. In the case, what happens in the case of protein? If you take a protein, for example, that has a good resolution, this is a case of a protein which is called papain, then you see that the resolution at 2 angstrom, which is a fairly good resolution. It's not brilliant, but it's a good resolution. You can measure something like 25,000 spots. But then the protein has, if we do not consider the hydrogens, because the hydrogens cannot be refined, the protein has 2,000 non-hydrogen atoms. That means that for each atom, you have to determine the X position, the Y position, the Z position, and then also the B factor that is a parameter that measures the vibration of your atom inside the crystal. And then if we have 2,000 atoms, that means we have 800 parameters. So if we make the ratio between our data, 25,000 in number of parameters, we have a ratio that is only about 3, which is much lower than the one that's expected to be to have a stable mathematical problem for the refinement. So, and if you have low resolution protein data collections, then you have, for example, a 3 angstrom resolution data collection, then the number of data is similar to the number of the parameters you have to define. So you have a ratio which is 1. So what is important, and this is something that it's very well known to crystallographers, but not to the people that use floating crystal structures, is that what you get from your experiment, when you do the experiment, the data you get are not enough to solve the structure. So are not enough, not to solve, I mean, to refine the structure to have a reliable model. And then, of course, you can get a problem with your fitting because you have too many parameters for too few experimental data. I have this small diagram that shows usually students which is the kind of problem you get. If you have 2 parameters, 2 physical parameters, X and Y, then you make measurements in which you fix, for example, the X parameter, and then you measure Y, and then you get this, for example, 1, 2, 3, 4, all this experimental data. You get all this experimental data, but what you want in science is not to make measurements, but you want a model that can interpret the dependence between X and Y. And you say, okay, in which kind of physical model I can derive from this data? Then I can do things, many things, but I can assume that the dependence of Y from X is a sort of linear dependence, like this one. But also I can, playing with mathematics, and you are, of course, much better than me. You can use this kind of formula. And if one asks you, which is the best fitting, of course, this one is much better because the agreement between the curve and the points is much better than here. Here, the discrepancy is much higher. But there is a big difference between the mathematical fitting and the physical connection between these 2 entities. How can I discriminate between which is the best fitting? And what we do, what has been really a revolution, now it's about 30 years ago, but a revolution in protein crystallography, but probably it was much used in other fields, was the cross-validation. And what does mean cross-validation? So how do I choose for the best model of fitting this one, which is simple in terms of parameters, or this one, which is better in terms of passing through the points? So the things that cross-validation works, probably much better than me this part, but you can take out some of your experimental points. For example, you take out these 3 points, and then you make fitting using all the other points. So you take out these 3 points, then you make the fitting with the other points, and then you get this kind of solution. The linear fitting gives us a line that's close to this one. It's not exactly the same when we use all points, but it's close. And this is the fitting. Then, of course, I can use some more complicated mathematical formula, which is this one, for example. This one is much better fitting than the linear one. But if I got the right physical connection between these entities, the model I derived, either this one or this one, should also be okay, fine for the points that I did not consider. That means the other 3. And what I see here is that, this model behaves very, very poorly for the points that are outside. This one is much better. So this, I don't want to explain you cross-validation, but it has been very important in protein crystallography, we will see later, because, and in these very simple examples, tells us that it's much better to use a simple model and not this one that also had the better fitting with the points that I use in the fitting, because I do not have enough experimental point to fix all these parameters of the curve. So this is something that, is the problem of overfitting, which is a problem that's sort of an intrinsic problem of protein crystallography. And so what do you do in this case? How do we solve this problem that we have too few experimental data and too many parameters that you want to determine? So the way is that you use some additional information. So you do not use only the structure factors, the experimental structure factors in your refinement, but you also use some information, because the sequence of your protein, which basically which atom is bound to which atom. And you also know something about, for example, two carbon atoms, which kind of distance they have. You know which kind of angle atoms make making specific bonds, which kind of diagonal angles they make. You know that there are some planar group inside the protein. You know that, of course, atoms cannot be everywhere. They cannot overlap each other. They should, they cannot compenetrate each other. So all these are restrictions to the possible solution of your structure problem. And then what do you do? Instead of refining only this part here, which was the one that we seen before, that, changes your structure factors in order changing the coordinates of the model to have structure factors that are as close as possible to the observed structure factors. They also include some geometrical terms that tells that your model has to have bond distance, bond angles that are as much as similar to the one that you are expecting. You have not make distortion in your structure. And these are the ways. Of course, you can weight in your function how importance you give to the structure information, which is important you give to the stereochemical geometrical information. These are the weights we were discussing before. Is this clear?
Luigi,
Yeah.
what is Q here? Q.
Q is the if you have the two atoms here, this is the equilibrium distance. That means that you expect that, for example, 1.5 is the distance between two carbon atoms, right? So you put this one is the equilibrium distance, and this one is the equilibrium distance, and this one is the distance you see in your structure. So your distance in your models for a given pair of atoms should always have should be always close to the ones that you have which is the restraint. I repeat just once. So this is the distance you have in your model, and this is the distance you have in your target function, which is the one that you expect for that kind of geometrical parameter.
Luigi,
so you have,
in this extra sum, Q is a pair of bonded atoms.
Luigi, Q in this example would run 1 through 5. It would be which of these types of constraints?
Yeah, exactly. I mean, the restraints can be a bond distance, but also a bond angle. That in principle you can make a distance between these two atoms, for example, so that are not bonded, but they are, or you can put a restraint. It's a geometric restraint in which all atoms should be planar. I mean, all this kind, but there are also many other. This is just an example. I mean, this is just the difference between the value of that parameter in your model and the value that is the ideal model that you have, that you expect. Then, of course, you can make a very good agreement between FCalc and FOBS if you give a big weight to this formula here, but then you can destroy the geometry of your system. That will be very different from the accepted values, or vice versa. You can do the same. So you see, the refinement is a sort of something you have to balance these two different terms, and you never know if it's done correctly or not, in principle. That's why you need to validate plot structure, because you do not have enough data to solve. In small molecule, you do just like this one. You do not use any a priori information like the geometry you use in plot. said in another way, the experimental data you have for protein structure determination are not enough to, to accomplish your task. Is this clear?
Yes.
Okay.
Thank you, Luigi.
Yeah, this is the actually value were also reported here. So, and at the end of the process, you measure the difference between the structure you use as a validator of your structure, which is called R factor. The R factor is exactly the difference between the observed structure factors and some more weighted, but doesn't matter, the calculated structure factor, right? But you can see that this value is not very a very good indicator, because if you make a refinement in which you put a very small weight here, then of course you can minimize this difference and then you can get very low R factor. Is this clear? You can minimize as much as you want this difference, just if you put a very small weight to the geometrical part. So of course, when you minimize, then this one will be similar to this, and the R factor difference will be low. So this was so you have to be sure that your model is also not only has a very good R factor, but has also a very good stereochemistry. Should also have a very low difference for this term. And this was sorry. Yeah.
Luigi, so these coefficients or parameters W from your previous slide formula, are they universal constants or
no? You have to actually there are many ways. We probably can have some insight later, but you have to fix system by system. And what actually I will show you, we'll come back on this if you want later. There are some rules that you can use to, but of course there are parameters that are system dependent parameters.
By one way dependent, you mean dependent on a given molecule, on a protein? Yeah, depending on the data you have, but I will show well, I use one criteria which can be used by the other. Which is the kind of dispersion you can have for the geometry, for example. And then, of course, if you see that your system is too much relaxed, distances are not very close, you can increase this parameter. I mean, it's something that depends much on the user. And then there is one factor which is called the R3, which is very important, that we will see now, that you will find in any structure elimination. So the R factor is an indicator, but you can reach very low R factor just by destroying the geometry, just putting a very small weight here, and then of course this will not be important for the function, for the minimization. So there have been in the 90s some very bad structures. Those are some famous examples of wrong structures. So when things start to be problematic in protein structure elimination field, then you see here, this was a paper appeared in Nature. It seems that, I don't think we'll go much further. So you see here, there was a big problem in the structure determination there were many errors in structure determination of proteins. And there was this very big advance in protein crystallography, which was called the R3. The R3 was exactly a cross-validation approach in which the R factor was calculated on some structure factors that were not included in the refinement. Is this clear? So Luigi, what's the difference between the formulae? R factor and R3?
Is exactly, the formula is exactly the same, but the spots in which you use this one were used in the refinement, so they were used in the minimization. This one were not. It's like the points that you use in the fitting. It's like the formula is the same, but it's like these points here are used for calculating the R factor. So are points that are not used in the refinements. So they are not used to define the model. But then in the end, you still measure, for example, here the distance with the curve. So I mean, so you measure, it's like in this case, you measure the distance with the curve of the points that you use in your fitting and the points that you don't use in the fitting. Okay. And this made a very big difference. So the formula is exactly the same. The formula for the R factor and the R free is exactly the same, but these one are reflections that have been used in the refinement. These one are reflections that have been just not neglected. But then in the end, when you have your model, then you calculate the difference also for these ones. And then they could see, and it's clear like that you can get very lower factors, but you can usually have, if the model is wrong, these R free will be pretty high. And then of course we'll tell you that model is not reliable.
Luigi, these R factors, do they make sense only for protein structures obtained by X-ray diffractions, or also for cryo-EM?
No, I mean, no. That's a parameter, because this is actually what you get in every crystallographic structure. So those are parameters. So what I wanted to show you was exactly, because this is a table that appears almost in all X-ray structure paper. And then I want to show you what is the R factor and what is the R free. And of course, since they are based on difference between structure factors, are of course parameters that are used only for the X-ray structures. You see, R free is always a little bit larger because, of course, there is always a bias of the model. And this one tells us that the structure is good because the R free is quite small. Okay. You could have, for example, if you get here something like 0.20 for the R factor, which is not bad, but here you get 0.40 or 0.50, then the structure is wrong, even though this one is correct. It's like, you know, you have just fitted the noise or something like that. You have overfitted your data. And this actually was really a big difference. These are the discrepancies here about the ideal bond angles, the one that you expected, that you knew, and the one that you have in your model. So it tells you something about them. So these is something that tells you how the geometry of your system has deviations with respect to the ideal one.
Mm-hmm. Luigi,
and, you know,
for computing R-free values, some data is hidden or missed.
Exactly. Yes. For cross
what proportion is missed?
Okay, that's an important question. Of course, you know, every time you make an experiment, it's always a pity not to use all the data. So because, you know, a big effort sometimes needed to collect data. So usually in protein crystallography, we use about 5–10% of the data are hidden, as you said, are not used for the refinement. But at the end, you do the refine when you are sure about your model, then you do the last refinement with everything. So when you do not have doubt about your interpretation, you use all the data. Well,
okay, so 5 or 10% are missed, but could I check this percentage which is removed? Is it chosen randomly, and how many?
Yes, of course it has to be chosen. There are programs that I don't know if you're an expert about the Ewald sphere, which, you know, tells you where the reflections are. Then they are chosen randomly about resolution and about intensity, and I mean they're just random, of course. Otherwise, you will have a bias in your model.
This random choice, do we make it once or several times?
No, you have to make only once at the very beginning. Otherwise, I mean, because of course refinement is a sort of iterative process. You do it many times because you change something, then you refine again, you change something, you refine again. Of course, your data the hidden data should have never been used. Otherwise, you know, your model has been in some stage influenced by those hidden data. They should be taken out from your experimental ensemble at the very beginning, and then only at the end you will put when you say okay, my model is correct, and then you calculate this other factor, and then at the end you can do a final refinement with your data.
So Luigi, this R3 is computed from one experiment. We remove randomly, say 5 or 10%.
Yes, no, you calculate the R3 in each step of refinement. And this is important because you see if the R3 decreases, then the modification you have done for your model is probably a correct one. You are going in the right way. The R3 actually is more important in the course of the refinement because it tells you if you are also about the weight. You could choose the weight by minimizing the R3. That's one way that sometimes I use. The weights you mentioned before, how you choose the weight of the stereochemical parameters and the structure factors, the experimental data. One way is that okay, I just change them. Then if I do get a lowering of the R3, that means that I'm going in a good direction because there is no bias on the. Is this clear?
Yes, thank you, Luigi. Yes, sorry, many questions. We are a bit over time already. Let me finish the talk. So please, if you
but I don't think we will be able to finish the talk. In any case,
no, actually, no problem.
So just to show you that. Sorry.
If you would like to continue next time, this is also possible.
Yes, of course. Why not? We can just finish about the story. Let's say in this way. Just
let's summarize for today.
Yeah. So there were many bad structures you see here. So people start to think we should make something to avoid this kind of errors. This was one big advances was the introduction of the cross validation in the field. That was introduction of this R3. This is a typical, as I said before, this is a typical table you get in all crystallographic structures of proteins. So, I mean, we could go in details of all these parameters, but I just want to show you which are the most important, which are the R3, and of course, the resolution of data and many other things. And, but for example, about 15, 20 years ago, there was another big problem. There were several structures that were wrong. They were published in this very high important journal, but they contained significant errors. Actually, the backbone of the protein was traced in a wrong way. And you see, so they had to retract retract these papers. And you see, but the crystallographic community is very tough. They made a motivation. Of course, they asked. They apologized for this big error because those papers were cited about, some of them even 400-500 times in few years. And so they mentioned that the error was caused by a program in which they switched some structure factor calculations. But then there was a person, a very old and influential crystallographer, who said that their justification was not in line with the errors they made. So, you know, even the retraction was in some sense debate. So, I mean, the community is very tough, and you know, usually this kind of proteins, I mean, they are nicely checked. Usually these are the parameters used for protein structure validation. So one way is to check, for example, bond angles. You see if bond angles and bond lengths are those in line with those expected on your final model. Then the omega angle, which is an angle on the backbone chain, should be close to, should be planar, so should be either 118 degree or 0 degree. So it should be either trans or cis conformation. And this is what's called Ramachandran plot. you can describe the polypeptide chain. These are the bonds inside the polypeptide chain. This angle here, the hydral angle is called phi. This one is called psi. Of course, if you just rotate phi and psi, not all combination of phi and psi are allowed because you can get some clashes. And those are the regions that are allowed here. Those are very much allowed. This one are generously allowed. This one are some way forbidden. And then when you take a protein, you calculate the hydral angles for all residues, and then you check that those actually are inside in the allowed position of the Ramachandran plot. This is probably the most used and the initial check of your structure. So if you have something in the wrong place, but this is not exactly what is important. Of course, you have many other parameters. Of course, atoms should not overlap with each other, and then there are many other parameters. Just I want to show you that all these are anyway, when you notice something strange, it's not necessarily an error. This can be just an outlier. Then you have to decide whether in an unusual situation is an error or is an outlier, because in some situation you can have a sort of convergence of chemical physical factors that brings all the system in a strange way. So you have to go back to if you look something, for example, a strange angle, a strange conformation, then you should go back to electron density and see what actually the crystallography. So, for example, we made this is Ramachandran plot. As we said here, for example, atoms are not, residues are not allowed to be there. But then you see here there is a repulsion between this atom, which is carbon, beta carbon, with the rest of the chain. So here it's not, in the Ramachandran plot, this region is not allowed. But then we made a mutant forcing the residue to assume that conformation. We made the electron density. We see clearly the electron density, and then you see the conformation was here because, of course, you can get. This was a typical example in which this one is an outlier. It's not an error because we did on purpose. We were able to put a residue in a situation which is not normally allowed in Ramachandran plot, but this was because the local constraints allowed it. So in principle, you should be always aware of the difference between outliers that are those that you find in the validation step. And then if the electron density does not justify such a strange situation, then they are errors. And of course, there are all validation servers, but if you want, I don't want, I don't want to bother you more. If you want, we can continue in the future, whenever you like. Yes, unfortunately, I took this way just because otherwise, I thought it would not have been useful to go into many details.
Yes, but, Luigi, thank you very much for your introductory talk. Let us thank Luigi.
Thank you.
Yes, thank you very much for your great introduction. Since we're over time, does anyone have a quick question for Luigi? Luigi, would you like to continue your talk?
Why not? But it takes 1/2 an hour at least. If it's enough, I can. Or we can continue in another occasion.
It will be completely enough because we will have questions. So more questions. So
sorry.
We will certainly have questions on your slides. So even if you repeat some of them, I am pretty sure we will have questions to discuss.
So which is your choice? Should I?
Will you be available, for example, next Friday?
Probably in a couple of weeks, yes.
In a couple of
weeks. I don't know, in a couple of weeks,
okay.
Yes, of course, because now everything is ready. I have the presentation ready, so we can continue the second part, and then we can go on more details. And if you have some questions, you can also write me so I can, prepare answers, or even the organization, or if you are interested in some specific topic, if it's something I can handle, I will.
Yes.
Okay.
So I'm finally